other than my first lecture. So if you're an expert in Tikhonov regularization, then this will probably be very boring for you, but I hope that at least some in the audience are not familiar with regularization yet, and then I hope this will be a nice introduction for you. So what I will show you here is basically the main idea of Tikhonov regularization, what I would say started this subject of inverse problems to become an independent mathematical topic in the middle of the 20th century. And it's basically what you will get out of the, let's say, first of two chapters out of any textbook on the regularization of inverse problems. So let's consider the same setting as before. Let's say we have two Hilbert spaces and we have a linear and continuous operator between these two Hilbert spaces. And we think of this operator as mapping some kind of parameters, let's say the image of a patient, to the data that we can measure with a CT scanner, with an EIT scanner, or with blurred image. And what we want to do is we want to invert this mapping, and we assume that it is invertible, at least that there exists the left inverse, that A is injective, but it may be discontinuous. And as we have seen in the first lecture, this is the generic thing in inverse problems. Whenever you have an infinite dimensional problem, this A to the minus 1 will become discontinuous. And the general philosophy, if you treat inverse problems in practice, is that you try to find a way to cope with these discontinuous problems. And then if you have a way of stably solving these discontinuous ill-posed problems, then you can also use them on your discretizations, which will be continuous, but very, very almost unbounded. So you develop your strategy, we develop our strategies in infinite dimensional spaces, then we have a strategy for unbounded operators, for discontinuous operators, and they will help us also for matrices that are still continuous, but which have a very, very large norm. Think of something like 10 to the 16 as the norm of your inverse matrix. Then this is still continuous and strict mathematically speaking, but you need the same strategies as for an unbounded matrix. So we have the same setting as before. We consider a true solution. We consider some exact measurements on exact right-hand or here left-hand side of our equation ax equals to y. We have given some noisy measurements, where noisy means that the distance to the true measurements is smaller or equal than delta in the norm of our y space. And we know that if we have the exact measurements, we could calculate the exact inverse of that. We could exact our true solution, but we don't have exact measurements. So how can we approximate our exact solution for noisy measurements? And just inverting our problem as good as possible would mean we use the exact left inverse, and we have already seen that this fails. And let me go into more detail here. So first of all, the problem using the exact left inverse may fail for mathematical reasons, because this exact left inverse may not be well defined for what we measure. So this is then more of an academic and mathematical problem. So maybe our data that we have, it's in the range of A, we believe that there is a patient, that there is a true solution, but if we add some noise to what we measure, then maybe we are no longer in the range of our operator. That's something that frequently happens. So A to the minus 1 y delta may not be well defined in a mathematical sense. And then, of course, we have this big problem of ill-postedness. Maybe it is defined, but A to the minus 1 is discontinuous. So this means we measure more and more accurately, but we don't converge against the true solution if you use A to the minus 1. And it may be even worse. So generically, it's not only that we don't converge against the true solution, but we don't converge at all. We generically diverge. What we get if we apply our true inverse to the noisy data is something where the norm goes to infinity. And the reason is that our A to the minus 1 is an unbounded operator. So this means that if we plug in a sequence of vectors, the resulting image vectors may become arbitrarily large. And that's really something that we often see in practice. If we have some kind of noisy measurements, if we put this into if we try to solve our problem as exact as possible, then what comes out is an image which has extremely large values to the plus and to the minus side, so it's something like 10 to the power of 8 plus 10 to the power of minus 10 to the power of 8 on the minus side, for an image that should have values between 0 and 1, for example. So usually we do not only not converge if we solve our problem as good as possible, but we also go to infinity with what comes out if we try to solve our problem as good as possible. And we don't want that, of course. I mean, we want to approximate our true solutions from the noisy measurements. And of course, we cannot ask for getting the exact solution out of noisy measurements. That would be too much. But what would be a mathematically realistic goal or a nice goal if we could accomplish that is that if we have noisy measurements that get more and more accurate, is there a way to get a sequence of approximate solutions that get more and more accurate? So from the sequence of y deltas converging to y, is it possible to get a sequence of approximations x delta that converge to the true solution when delta goes to infinity? And if we have this, then we can tell the guys from practice, if you just measure accurate enough, you can get as close to the true solution as you want just by measuring more and more accurately. So this would be a realistically nice goal. So what we are looking for is some kind of a reconstruction formula where we put in our measurements, where we will see that we also have to put in the amount of noise that we have, the delta, and what comes out should converge against the true solution in the limit of the measurement noise going down to 0. And note that using the exact inverse does not work. And I mean this usually if we talk to guys from practice, they usually think that the best thing they can do is taking the exact inverse. And if they don't take the exact inverse, then it's because of discretization, it's because of computational things. But they think that they are doing good if they use the right inverse, and they are not. Because if you use the true inverse, even the mathematically perfect inverse, this will not converge against the true solution. I cannot stress this enough. And what we will see in this lecture is just a very basic idea of linear Tikhonov regularization, which gives us an explicit formula how to get something that converges against the true solution. So we will see that if we use a to the minus 1, and we have seen if we use a to the minus 1, it does not converge against the true solution. But if we use this guy here, so a star a plus some small constant times the identity up to the minus 1 times a star times y delta, and if we choose this constant to be the same as our noise level, then this guy will converge against the true solution. So we have a possibility to get the true solution out of our noisy data, but we are not allowed to use the true inverse, but we have to use, for example, this guy here. And this lecture will be just basic math, proving you this last formula on the slide. So I will try to motivate where does this formula come from, and I will rigorously prove that this formula holds true and that we have convergence for delta going to 0, so that there is something that converges against the true solution, even if the true inverse does not have this property. So, where does this formula come from? Why should we use something like this a star a plus delta I up to the minus 1 times a star? Well, what everyone would usually do is, if we want to solve ax equal to y, and now we don't know the y exactly, but we have something like y delta, then usually you would try to solve this equation, and if it's not exactly solvable, this equation, then you would be fine with that, and you would say, okay, then I try to solve it as good as possible. So what people from practice usually try to do is they try to minimize this residuum here. And if a is invertible, then you choose a to the minus 1 times y delta, and this is obviously the minimizer of this function. And that's what people usually use in practice, and if you have someone from practice and you ask him whether his method works, he usually shows you a plot of this guy here, the residuum, and then you see his method, this residuum goes to 0, and then the guy believes that if he found a minimizer of this residuum, or if he got this residuum very, very small, then he believes that he has found a good x. And he doesn't. Because we know if you have the true minimizer of this is a to the minus 1 y delta, and this is not a good solution for our problem because it can be arbitrarily far away from the real solution. So if you look at the residuum for an ill-posed problem, it doesn't tell you whether your solution is good or not. If your residuum may be small, 0, but still your solution is completely crap. And in all the images I showed you, remember we have this right-hand side, we added some noise, we used the exact inverse. This exact inverse is the minimizer of this functional, and it was obviously not useful in practice. So using just minimizing this functional is not a good idea for an ill-posed problem. Now what else could we do? We know that what happens, or what usually happens, also we could have seen this maybe in the images I showed you, is that if you take the minimizer of this functional, then this is something like a to the minus 1 by delta, and this may be arbitrarily large because a to the minus 1 may be unbounded. And you usually see this in practice by some really high values that are not realistic. So this means if you just take the minimizer of this, your x will become much too large. The norm of x will be much too large. So the first idea we could have is, can we somehow prevent this and also have the norm of x be small? So this would be some kind of a multi-objective optimization problem. We want the residuum to be small. Our parameters that we get out, they should fit to the measurements, of course. I mean, they should have something to do with what we measure. But at the same time, our parameters, our image that comes out, shouldn't contain any unrealistically high values. At the same time, the norm of x should also be small. And then we cannot solve multi-objective optimization problems without deciding how important is one objective compared to another objective. So the easiest way of getting both things small is to try to minimize the sum of both terms. And then, of course, it's much easier. So minimizing this thing here is getting more complicated in a computational way because we have some kind of non-differentiable points because of this norm. So this is an absolute value. They would have a non-differentiable point around 0. And it's much easier if you don't minimize the sum of two norms, but it's much easier to minimize the norms of the squares. And since our motivation is that we want to have both things small, we don't care about whether we have up to the power of 1 or up to the power of 2, so we take the one that's computationally easier. And so this would probably make sense if we have something that minimizes this functional, then the residuum would not be too large, so this means it would fit to the data that we measured, and at the same time it would not be too large. But it's, of course, there's still a lot of ambiguity in there. I mean, if you think of it from a physical point of view, the units in your space y, the units in your space x, they may be completely different. And if you take, let's say, milliseconds instead of seconds here, then you will have a factor of 1,000 here, which will very, very much influence this functional. And so it doesn't really make sense to add something in the space y together with something in the space x. Or at least you need some kind of weight that controls how important, how large are the numbers in x, how large are the numbers in y, and how important is it for me to get this thing under control or to get that thing under control. And that's what people do in Tikhonov regularization. You decide for a parameter alpha and fix an alpha, and then you try to find the minimizer of this thing here. And the alpha is a parameter. Well, first of all, you could play with that. If you choose your alpha very, very large, it means I'm looking for a solution that has a very, very small norm. In the limit of alpha going to infinity, the minimizer will obviously go to 0. So if you say alpha is almost infinite, then I say it's only important that my parameters are very smooth, are very small, and what comes out then, of course, is a 0 vector. And if you choose this alpha very, very small, alpha going down to 0, then this means I don't care how large my solution is. I just want the solution to fit nicely to the data. So if you take alpha equal to 0, then you just try to fit your data perfectly, but this also means that you're fitting your error, and this means that your solution will be unrealistically large and also be bad. And so what we hope is, if we have some nice parameter alpha here, then maybe for a nice parameter alpha, we will have something that's still regular enough, has a small norm, and fit to our data nicely, so that the minimizer for some alpha here will maybe be a good solution for our problem. And we will see that this really works. So, how do we solve this minimization problem? Well, formally, this is very, very simple, because we can write this minimization problem as a minimization as a linear quadratic functional minimization problem. So we have this functional with the two norms inside. We can write this as a minimization problem of just one norm. by constructing the space x times y. So we consider long vectors where the first infinitely many components are the components from x, the other infinitely many components are the components from y. And then minimizing this term here is the same as minimizing this expression here in the natural norm of x times y, which is the norm of x squared plus the norm of y squared, and then the square root of this. So we can write this together as a long vector in x times y. And so we have the problem of minimizing the quadratic functional in the form matrix times vector minus matrix should be as small as possible. And if this was finite dimensional spaces, then this would be something standard from a first numerical analysis course that you solve with the so-called Gaussian normal equations. And they tell you that you can minimize the residuum of such a linear equation by ax equal to b by taking a star ax equal to a star b. So you would need to know the adjoint of this matrix here, and then the adjoint of this matrix times x would be adjoint times the right-hand side. And if you just formally calculate this, then you would expect if these were matrices, then this would be the adjoint. And so we can write it like this. And if everything is okay and everything was finite dimensional, then we could multiply out these matrices, and this would give us this equation a star a plus alpha ix is equal to a star y delta. So this is where the Tikhonov formula comes from. If you take x as being the inverse of a star a plus alpha I times a star y delta, then what we get is exactly, and we prove this, is the minimizer of this functional here. And we hope that there is some alpha where this minimizer of the functional will be a good value for our solution because it fits to our data and at the same time it's not too large.
Excuse me.
Yes.
How to guarantee that alpha should not be a spectrum of a star a?
Pardon me?
You want to invert that a star a plus alpha, right? To get x.
I didn't get that. Just say it again, please. No, please.
You want to invert the operator a star a plus alpha, right?
Yes.
So alpha should not be in the spectrum of that operator, right?
Well, actually, we will prove that this is always invertible. I mean, the reason is a star a is always positive definite, so the spectrum is positive. If you add a positive alpha, then it's never in the spectrum. Yeah. But we will prove that. But you are completely right. We will have to make sure that this problem is invertible, and we will have to prove that. And we also have to make sure, I mean, I just had some formal motivation, that this is the same as what we have here, which is true, or you have probably seen the proof for that in your numerical analysis courses for finite dimensional spaces, but we also have to make sure that this is equivalent to this equation also in our infinite dimensional Hilbert space sets. So we will have to make sure of all of that, yes. So we add here, we are looking at this for positive parameter alpha. Of course, alpha equal to 0 is nonsense. We've seen that because that would be the exact inverse. So we believe that there should be some kind of parameter alpha where this thing is a good approximation to our solution. So, here we have it. The first problem we might have is, can we solve this equation? Can we find this minimizer by solving a star a plus alpha I, the inverse of that times a star y delta? Is alpha in the spectrum of the operator a star a, and may something go wrong there? And we will see it does not go wrong. This operator a star a plus alpha I, this is a nice operator in the sense that it can be inverted. And not only that, it's also not an ill-posed inverse problem, but it's a well-posed inverse problem because this operator really has a continuous inverse. And depending on how good you are in functional analysis, some of these proofs may look extremely trivial to you. For example, if you're familiar with the spectrum, then you see that a star a is a positive semi-definite operator, or the spectrum is larger or equal than 0, so you add some small constant alpha, so this shifts your spectrum larger than alpha, and then if you invert it, you're away from the 0, so you can stably invert this thing. But you can also prove this in a very elementary way. So let's start with the proof of 2.1. And by the way, so as Svenky told you on my webpage, I have all these slides, and I also have some lecture notes on these proofs. So if you don't want to write them, you could also look at them up in the back. So why is this operator invertible? Let's say we have some vector z and x, and we want to find out why can we have an inverse of a star a plus alpha I applied to z. Well, first of all, x and x solves a star a plus alpha I x equal to z if and only if a star a plus alpha I applied to x, and then the scalar product with some vector psi is the same as z and the scalar product with the vector psi. So just round brackets, I'm writing the scalar product in the Hilbert space x, and obviously if a star a plus alpha I x is equal to z, then this equation here is valid. And on the other hand, if we know that this here is valid for all psi, then we could bring the z to the other side and choose psi to be a star a plus alpha I x minus z. So then we would have some vector times himself in the scalar product. This would be the norm of this vector squared. So this is the same. So this is 0. A star a plus alpha I x minus z scalar product with psi is 0 for all psi. Then we can choose the psi to be the left hand side. This means the left hand side, the norm must be 0. So this means that if this holds true for all psi, then this left hand side of the scalar product must be the same. And this is a form of a variational equation that you've seen many times in your PDE courses, for example. So what you see on the left side is a bilinear form that takes two vectors from x and makes it into a scalar. What you see on the right hand side is a linear form that gets one vector of x and takes and maps it to the real numbers. So b goes from x times x to r. It's obviously bilinear. And we can also write it in the way that we take one of this a star and take it to the right hand side of the scalar product. And this is ax, a psi. We take out the alpha I, so plus alpha x psi. So we immediately see that b is also symmetric with respect to x and psi. And we immediately see if we plug in x dot x comma x, then we will get ax, so the norm of ax squared, which is something non-negative, plus alpha times the norm of x squared. So this means if we have bx comma x, then this is larger or equal than alpha times the norm of x squared. So this b is symmetric, it's obviously continuous, and it's also obviously coercive with a coercivity constant alpha. So b is symmetric, continuous, and coercive with a coercivity constant alpha. And the right hand side, the L, is obviously a linear mapping from x from C to the real numbers. It's obviously continuous, it's obviously linear. And the norm is smaller than the norm of z, because we can bound by the Cauchy-Schwarz inequality the scalar product by the norm of z times the norm of psi. And if we put in z comma z, then we really get the norm of z squared. So this means this norm is really the same, not just smaller than that, really the same as the norm of z. And then we can use the theorem of Lax-Milgram, which tells us we can we have a solution of these kind of variational equations. If we have a bilinear continuous symmetric coercive bilinear form and a continuous linear right-hand side, then for each continuous linear right-hand side there exists a unique solution x of this kind of equation. And Lax-Milgram also tells us that this dependence is a continuous one from the right-hand side to the x, so that we can bound the x by the norm of the right-hand side, and the continuity constant that comes in is 1 over the coercivity constant. So our continuity constant that comes in is 1 over alpha. So Lax-Milgram tells us that A star A plus alpha I is continuously invertible. We have a solution of this equation that continuously depends on the right-hand side, and the norm that bounds our inverse is bounded by 1 over the coercivity constant. So this means we can continuously invert expressions like that. And of course, we could make exactly the same arguments if you don't look at A star A plus alpha I, but if we look at A star plus alpha I, then we have exactly the same thing with Y instead of X and A star instead of A. So analogously, we can prove the same thing for A star A plus alpha I. So instead of solving Ax equal to y using this unbounded inverse A to the minus 1, we have replaced this by the bounded inverse of A star A plus alpha I. So at least we have now replaced our ill-post problem but by a well-post problem. But of course that's not everything we want. We don't only want to replace an ill-post problem by a well-post problem, but our solutions should still have something to do with the solutions of the original problem. So we have to see whether how good are the solutions if we use this operator here. How much do they have to do with the true solution that we are looking for?
So in what context do you use A star A, and in what context do you use A star?
So far we have only used A star A. But it will be useful in a later proof to also use A star. And there's also, I already mentioned this here. So the solution of this so far, we only use A star A plus alpha I up to the minus 1 A star y delta. And there's a nice numerical trick. If you do this in practice, this thing here is the same as, you can easily show this, as putting the A to the other side. So this is the same as having, let's see, I hope I make this right, A star plus alpha I to the minus 1 y delta. Let's see. So you can easily check that this holds true. And in your numerical calculations, it's sometimes useful to use this thing here, because the matrix you have to invert has here the dimension of A star A. So this thing here is an operator going from X to X. So if you discretize this, then you will have a matrix that has the dimension of your parameter space. And usually you're looking for images. So usually you have a very high dimensional discretization of X, which is like if you take 100 times 100 pixels, you already have 10,000 unknowns, and you don't want an image to just have 100 times 100 pixels. On the other hand, this operator here, A star, this is an operator going from Y to Y. And in many cases, you don't have so many measurements. So if you don't have so many measurements, then you have a low-dimensional discretization, or rather low-dimensional discretization of Y. So if you have a couple of measurements and you try to get an image from your couple of measurements, like a very underdetermined system, then this will be a small matrix, and this will be a very large matrix. And the easiest thing to do in your numerics for Tikhonov is that you can decide whether you want to solve a problem, a matrix vector equation of the matrix having the dimension of your parameter space discretization or of your data space discretization. And usually the data space discretization is smaller. So this is something that can help you in the discretization later. But mathematically, they are completely equivalent. So now we have seen that we can stably solve this Tikhonov equation. Now, how about this minimization property? Is what we have here really the unique minimizer of the Tikhonov functional? So the formal arguments coming from the finite dimensional numerical analysis course, do they also hold true in this case here? So that would be proof of this theorem. And again, this is a very simple and elementary proof to see. So let's give the things a name. X alpha delta should be this guy here. And then we know that for all x in x, we can compare how large is our functional if we put in x alpha delta, and how large is our functional if we put in any other x. And if we can prove that if we plug in x alpha delta, the functional will be the smallest, and we have proven that this guy here is the minimizer of the functional. So we will compare our functional. Let's write it this way: y delta minus ax squared plus alpha x squared. So this is our functional with any x inserted. Then I subtract the same functional with this guy here inserted, x alpha delta. So y delta minus ax alpha delta squared minus alpha x alpha delta squared. And then we can multiply the square with the enormous formula. We have real Hilbert spaces, the scalar product is symmetric. So it's like using then the binomial formulas. And then we have y delta squared here and y delta squared here. So this cancelled out. And what we end up with are the mixed terms. So we have minus 2 times y delta times ax. And then we have ax squared, and we can put this together, the alpha x squared, and write this as x times a star a plus alpha I x. In the scalar product, so if we take over 1a, then we have ax plus alpha xx, so this is the ax squared plus alpha norm x squared, what we have in here. And then we have the same with this expression, the y delta squared cancelled out, and we have 2 times y delta ax alpha delta minus x alpha delta a star a plus alpha I x alpha delta. So I'd like to take these two guys together, and I want to bring in x minus x alpha delta, because if I assume that x is not x alpha delta, then this should be larger than this thing, if the assertion is correct, and x alpha delta is really the minimizer. So what I would like to have as a term is x minus x alpha delta times a star a plus alpha I x minus x alpha delta. And if you multiply this out, then you get this term here, which is fine. And then you get the mixed terms here that we don't have in the line above. So we will have to add or subtract them in order to make these things equal. So we need the mixed terms, 2 times x a star a plus alpha I x alpha delta. Then we have this 2 terms here, minus 2 y delta ax and plus 2 y delta ax alpha delta. And the last term that comes from multiplying this here out, has the wrong sign if you compare it to this term here, because if you multiply this out, you will have x alpha delta with 2 times minus or with a plus, but we need it with a minus, so this should be equal, and I have to subtract minus 2 times x alpha delta a star a plus alpha I x alpha delta. So then things simplify because x alpha delta solves this thing here up to the minus 1 a star y delta. So this is the same as a star y delta. And also this is the same as a star y delta. And then you see if you take the a star over here, this is the same as this guy, and this is the same as this guy. So everything except the cross term cancels out. And this cross term you can also write as taking the a to the other side, a x minus x alpha delta norm plus alpha x minus x alpha delta norm squared. And then we see this term here is always non-negative, and this term here is larger than 0 if x is not x alpha delta. And this shows that if you choose an x that is not defined by our formula for x alpha delta, then the functional will be larger than if you choose x alpha delta. So this shows that our x alpha delta is really the unique minimizer of our functional that we have here. So we have replaced our ill-post equation by a well-post equation, and we have a nice motivation for what comes out of this ill-post equation, namely that what comes out of this ill-post equation solves such a minimization problem where we have control over the data misfit and the regularization of our solution all at the same time. We still have to choose alpha in a correct way, to find out how to choose alpha and to study if we choose alpha in a correct way, do the minimizers of this function here correct against converge against the true solution. So in order to do this, I need one more auxiliary theorem, and that's this thing here. And again, this is a theorem that, depending on how familiar you're with functional analysis, you can prove in one line in your head. So if A is injective, then you can easily see that A star A is also injective. And if you have an injective, A star A is also safe adjoint. So the range of A star A is the orthogonal complement of the range of A star A would be the kernel of A star A, and this is 0 because A star A is injective. So this proves that A, range of A star A, stands in X. And also B can be proven in one line if you're familiar with V convergence. If you assume that A star A is compact, which it is very often in practice, then if you have a bounded sequence where A star A applied to this sequence converges to A star A applied to some other vector, then this bounded sequence would have a weakly converging subsequence. The compact operator would take the V convergence to real, convergence to strong convergence, so you would have A star A strongly converge, and then it has to converge against A star AX, and so this means that your weak limit must be X, and then you would have to try to argue that this weak limit is also the strong limit. And again, this can be, you don't need all this functional analysis for that. You can also prove this in an elementary way. Let me do this for you. The proof of theorem 2.3. So the range of A star A, if this was not dense in X, then there would be a vector in the orthogonal complement. So then there exists a vector X that's not 0 with X in the orthogonal complement of the range of A star A, which means that whenever we take the scalar product of X and something that comes out if we use A star A, this would be 0 for everything that we plugged into A star A. And then we can choose this psi to be equal to X. Then we have X, A star AX equal to 0. This means the norm of AX squared is equal to 0. But so this means AX is 0, but A is assumed to be injective. So this means that X has to be 0, and this is contrary to our assumption. A is injective. This means X is equal to 0. And this proves A. Part B will be very useful in order to, if we have something, I mean, that's exactly what we do in this Tikhonov regularization thing. We have some kind of convergence of the residuum, so we don't have convergence of, if we just take a to the minus 1 of our noisy data, then this fits, if we take these parameters, then they fit our data better and better. If we have alpha going to 0 in our Tikhonov functional, then we fit our data better and better with what comes out. So we have convergence, maybe not of X, but we have convergence of AX, of A star AX. So we have convergence in the image, we want to have convergence in the pre-image, and what we have by using the Tikhonov functional is control over the norm of our pre-image. This part B shows that this is really enough. If we have convergence in the image and we have control over the norm of the pre-image, then this is enough to get convergence of the pre-images. And let's also prove this. What we will first look at is what the scalar product between X and XK does. And to do this, we will first look at the following. Let's look at the scalar product of X and XK minus X. And we can say something about this. Well, we can use A, that the range of A star A stands in X. So this means we can approximate this X arbitrarily good with something that's in the image of A star A. So this is the same as A star A times Z, some Z. And then of course I made some error because I couldn't approximate it very good. So if I have to add the triangular inequality, I have to add X minus A star AZ XK minus X. And this holds true for any Z I put in here. And now we have an A star A here, which is fine because we know something about A star A XK minus X. So we take the A star A to the other side and use Cauchy-Schwarz inequality. And this is smaller than the norm of Z times the norm of A star A XK minus X. And this guy here, we have control over X minus A star AZ because we can choose the Z because the range is dense so that this is very small. So this is smaller than the norm of x minus a star a z. And this thing here is smaller than the norm of xk plus the norm of x. And we have assumed that the norm of xk is smaller than the norm of x. So this guy here has a norm that is smaller than 2 times the norm of x. So now we can, this holds true for any z. So the second term here, we can make it as small as we want by choosing the right z. So by choosing the right and appropriate z, we can make this thing arbitrarily small. Say for the right z. And then if we choose z in such a way that this thing here is as small as we want it to be, and this is completely independent of k. So for this z, we can then choose the k to be large enough. We know that a star a xk converges against a star a minus x. So for this z that we need to have the second term small, we can choose the k in such a way that this norm here together with the norm of z also becomes as small as we want it to be. And so in the end we have everything as small as we want it to be. So this gets arbitrarily small for fixed z and sufficiently large k. So this means that this term gets as small as we want if we choose k large enough. So this means that this term converges to 0. So we have shown that xk minus x converges to 0. And this means that x comma xk converges to x comma x. So this means that x comma xk scalar product converges to the norm of x squared for k going to infinity. And that's enough to prove the assertion, because then x minus xk is square this, and this is x squared minus 2 xk plus xk squared. And we have our assumption that the norm of xk is smaller than the norm of x. So this is smaller than the 2 times the norm of x squared minus 2 xk. And this converges to x squared, so this converges to 0, which shows xk converges to x. So this means that we have control over the images and we have control over the norm. Then we have we can get convergence of the pre-images. And that's all we need in order to prove convergence of Tikhonov regularization. So let's summarize this again. We have an injective operator. Think of a compact operator, but we don't need it for the math. Where we have a left inverse, but this left inverse may be unbounded. If it's not unbounded, Tikhonov still works, but then you don't need Tikhonov. If you have a bounded inverse, you could as well take the bounded inverse. But you don't do anything wrong if you take Tikhonov for a Weilbruch problem. That's also a good thing to know in practice. So we have this injective problem with an unbounded or possibly unbounded left inverse. We have the exact solution xz. We have a sequence of noisy measurements that tend to the exact right-hand side when delta goes to 0. And then if we choose the regularization parameter in such a way that it goes to 0 for delta going to 0, but not too fast, which means that what we need is the delta squared over alpha will go to 0. So delta squared goes to 0, and alpha should not go faster to 0 than delta squared, so that this term here still goes to 0. And for example, we could pick alpha of delta equal to delta. And this is that both things are fulfilled. If we put our alpha delta in such a way that it goes to 0 but not too fast, then with this alpha, our Tikhonov solutions will converge against the true solution. And let me at least try to give you the main idea of the proof also here. So the proof of 2.4. So first of all, let's give this long thing here a name. So R alpha should be the operator A star A plus alpha I to the minus 1 A star. And again, X alpha delta should be what comes out of our Tikhonov regularization approach, R alpha applied to our noisy data Y delta. Then we do essentially the same as we did for the finite differences. For the finite differences, we looked at how large is the error that we do if we use our regularized inverse compared to what we want to find. So we want to know how big is the error that we do if we use Tikhonov regularization with parameter alpha on measurements with a noise of delta. And we want to know how far are they away from the true solution of our equation with noiseless data. And what we did for the finite differences is we put in the finite differences applied to the exact right-hand side. So we do exactly the same thing here. We put in what would happen for x alpha delta as the regularization applied to y delta. And we put in what would happen if we would apply our regularization to the true right-hand side. So what would happen if we put in R alpha y hat here and triangular inequality plus R alpha applied to the exact right-hand side minus x hat, and x hat is the true inverse applied to the exact right-hand side. So this means, and this is usually called the regularization error. So what error do we do if instead of taking the true inverse, we take our regularization? So this is usually called the regularization error. And what we have here is usually called the amplified noise, because we can bound this by the norm of R alpha times the norm of y delta minus y hat. So this means we have some noise and it's getting amplified by our regularization operator, which has some norm, where the norm goes to infinite and alpha goes to 0. So this is the amplified noise. And the big idea is that if we choose the alpha very small, we can get the regularization error to be very, very small. Because if we let alpha go to 0, then at least heuristically we would assume that in our functional the alpha plays no role. So what we are minimizing is the residuum, and minimizing the residuum means taking the exact left inverse. So for alpha being very, very small, we have a very, very small regularization error. And the second term will go to 0. But on the other hand, if we choose the alpha very, very small, then our continuous regularization operators will approximate our unbounded inverse. And we have seen that this means that R alpha, the norms, will get worse and worse. Our regularization operators, the norms of these operators will tend to infinity if we choose alpha smaller and smaller. So this means if we just choose alpha very, very small, then this guy here will go to infinity. And what we have to do is we have to choose the alpha in such a way that it goes to 0, so that this guy goes to 0, but that it goes slower to 0 than the delta does. So we have the delta going to 0, so R alpha may go to infinite, that's okay, but it has to go slowly enough to infinite such that multiplied with delta, it still goes to 0. So we will show that the norm of R alpha can really be calculated analytically. We can show that it's 1 over the square root of alpha. And we have to show that R alpha y hat minus x hat goes to 0 for alpha going to 0. And if we are able to show this, then we have proven the assertion, because this means if alpha goes so slowly to 0 that 1 over square root alpha times delta still goes to 0, or delta over delta squared over alpha goes to 0, but alpha still goes to 0, then both terms will go to 0, and this means that our total error will go to 0. So everything we have to do is we have to choose the alpha in such a way that this amplified noise still goes to 0. So if we approximate the true inverse, we will have a higher and higher noise amplification. But if we adjust this to the level of noise, then the noise going to zero, amplified by larger and larger alpha, will still go to zero. And everything you have to do is to choose this alpha in the right way. And for example, alpha equal to delta always works for Tikhonov regularization. So these things are simple to prove, but since I'm running out of time, I will not show you the proofs of that. I have them also on my web page, and they are not really longer than this thing here for A and for B. So actually it's some simple calculations to get this 1 over square root alpha here, and it's not too hard calculation to get this thing here. So I will not prove you this, but rather show you some examples of that. So here's the image deblurring example. And let me stress, so I didn't use any kind of fancy modeling for the image deblurring. So all I used was the MATLAB command to blur an image. So in this MATLAB command, I put in images that consist of just one black pixel and the rest is white. And I did this for all pixels in a 100 times 100 image. And in this way, I generated a matrix that takes one image written as a long vector and makes it to a blurred image written as a long vector. So I really looked at this as like a generic inverse problem without knowing any mathematical properties of blurring, just having some kind of black box function making one image to a blurred image. So then I have this blurred image. I contaminate it by a little bit of noise, something like 0.1%. And if I then take the exact inverse of my matrix, I get complete nonsense. But if I don't take the inverse of my matrix, but if I take A star A plus delta I to the minus 1 times A star Y delta, what we get out is something that's at least a little bit sharpened. It's not as good as the original sharp image. I mean, there is noise on that, but it's a better image than the blurred image. And of course, you can get even better images if you really study the math behind blurring, if you know much about the blurring process. You can do it in a much more computational efficient way than adjusting for every pixel, and you can get much better images out of that if you do some regularization that's really adjusted to your specific problem. But if you just treat it as a black box index problem, that's what comes out if you take the exact inverse, that's what comes out if you take the Tikhonov kind of inverse with the noise value put in for alpha. And here's the same thing for the inverse Radon transform. Again, I didn't use any properties of the Radon transform. I used the MATLAB implementation of Radon. The MATLAB function Radon is a black box direct problem. Made the same thing pixel-wise to put this in a big matrix. Invert the problem as good as possible by inverting the matrix. If there's nothing good coming out, or inverting the problem using the Tikhonov regularization with alpha equal to delta, and out comes something good. And again, you can very much improve this by taking specific properties of the Radon transform, doing something like filtered back projection, where you really use specific properties, images will get even better. But I think this is really impressive to see how Tikhonov works on black box inverse problems. So let me give some conclusions and remarks for that. So again, I cannot stress this often enough. If you have an inverse problem in infinite dimensional spaces, it's usually ill-posed, and this means that your best data fit solutions trying to invert the problem as good as possible will not give you the true solution. But if you use, for example, Tikhonov with alpha equal to delta, then you will converge against the true solution. So you have to solve the wrong problem in order to get the right answer out of that. If you solve the right problem, you will get the wrong answer out of that. What I showed you was really like the most simple part of Tikhonov regularization, choosing this parameter to be delta. There are more sophisticated ways of math to show why these are better. And one thing I at least wanted to mention is the so-called discrepancy principle. You can try to choose your alpha in such a way that your data misfit term is in the size of your noise. It's a very natural thing to do. If you think of this alpha going down to 0, then you would approximate your measurements better and better. And how good do I want to approximate my measurements? But I want to approximate them as good as I trust them. So it doesn't make sense to approximate your measurement to fit your data better than you trust your data. So fitting the data in the size of the order of delta is probably a good idea, and this can really be shown to converge in some sense faster than what I showed you. So So this discrepancy principle is usually even better way in practice. You would improve the pictures I showed you if you use the discrepancy principle instead of just choosing alpha equal to delta. Then let me at least mention what you can do in nonlinear inverse problems. The theory is much less complete for nonlinear inverse problems, but the general two strategies are you could first linearize, so you have a linear inverse problem, and then use a regularization strategy, Tikhonov for that. Or you can do it the other way around, first regularize then linearize, which means you write down a Tikhonov function. You can also write that down, the same idea for a nonlinear operator. But then you have a nonlinear minimization problem, which usually you could solve by some kind of gradient descent or Newton-type algorithm, which involves some kind of linearization. So we have these two kinds of strategies, first regularized and linearized, or vice versa. And then another thing I wanted to mention is what I showed you here, just use the norm of my two Hilbert spaces. And what we used here is regularization in order to get convergence against the true solution. You can also use regularization in order to pick out solutions that are better than other solutions in a certain sense. For example, there's a lot of research going on things like BB or total variation norms, where pictures that have some smooth, some sharp edges are smaller in a certain norm than pictures without sharp edges. So if you're looking for pictures with sharp edges, then there are certain norms that are better suited for your needs than others. So you can do a lot of playing around these norms that you have and will improve this very much. So again, thank you for listening.
So, your regularization strategy, the regularization strategy is most, the way I understand it is that for A star A is not invertible. It might have like a 6 specified conversion. So